So I wanted to ask, first of all, where everyone thinks Wyoming is in the grand scheme of wind power within the United States. And as you can see from this information from the Pacific Northwest Laboratories, Wyoming is currently ranked 7th. Now this takes into account a number of issues. It takes into account the wind power that's in each different state, the transmission lines, buildability of projects. So Wyoming's in the top 10. There are a couple of states ahead of us, but we have a lot of wind power that we can develop here within Wyoming. Pacificor is actually the generation arm of the company. Pacificor and Rocky Mountain Power are different units of the same company. Pacificor is the generation and transmission arm of the company, and Rocky Mountain Power is the delivery of power to individual customers, whether that's residences or businesses. So I might use them interchangeably, but I'm basically meaning the same thing. Now, with utility scale wind development, most of the wind turbines that Pacificor has built are 1.5 megawatts or 1,500 kilowatt models. Most of them are made by General Electric. And these are some of the specific information for our turbines. The tower itself is 260 feet tall. The nacelle will then sit on top of that tower. If the blade is fully in the upright position, then the entire height of the turbine, including the tower and the blade, is 380 feet. The turbine weight, which is that nacelle, which is the picture we just looked at, is just under 150,000 pounds. So that's quite a bit of weight that's up there. And then the blades, the 3 blades connected and all combined total 51,000 pounds. So we've got just under 100 tons of machinery at the top of these towers. The towers themselves normally come in 3 sections, and the tower weight, which is mostly steel, is 119 tons. And then the foundation, which is used to hold all this together, 636 tons, so about double the weight of the components. For the 1.5 megawatt turbines that we normally use, if the wind is less than 7 miles an hour, the blades will not even spin. In between 7 and 9 miles an hour, they'll start to spin, but there isn't enough power or isn't enough motion to actually start generating electricity. Once the winds get up to 9 miles an hour, then we start generating, and once the winds get up to 30 miles an hour, then that's when the turbine is at full capacity. And once again, these will vary based on the different models of turbines that you have. So at full capacity, at winds of 30 miles an hour and greater, a 1.5 megawatt turbine will generate 1.5 megawatts of power in 1 hour. As winds increase up to 60 miles an hour, what will happen is the blades will pitch. They'll start to turn to take less of the wind, but they'll still be generating full power. Above 60 miles an hour, the turbines will actually shut themselves off. It becomes too much of a strain on the machinery if their winds are too high, so they'll have to turn themselves off during those times to prevent malfunction. So I just went over a 1.5 megawatt turbine will generate 1.5 megawatts of electricity in 1 hour if it's operating at full capacity. And that full capacity is anywhere between 30 and 60 mile an hour winds. So when you take the number of hours per day, number of days per year, you end up with 8,760 hours per year. So a 1.5 megawatt turbine will be able to generate 13,140 megawatts of electricity at full capacity. So that means if the wind is blowing 30 miles an hour all the time for a solid year, that's what you could generate. Now, that usually doesn't happen. We get windy days, we get days when it's not as windy, wind speeds come into play. So that's where we come up with the capacity factor, which is a key term in the development and the operation of wind turbines. So the capacity factor is, if you're looking at a turbine, how much of its nameplate capacity, so 1.5 megawatts, do you expect it to generate in a year? And so I've put in a couple of different sample capacity factors, 20, 30, and 40%. So with a turbine generating at a 20% capacity factor, you'd end up with 2,628 megawatts power going up to the 40 number that you can see there. So to give you an idea of how much a megawatt is, the average U.S. household uses 11,000 kilowatt hours of electricity each year. So that translates into 11 megawatts of power. So basically one 1.5 megawatt turbine running at full capacity would generate enough electricity over 6 hours that generates the same amount of electricity as one average U.S. household would use in an entire year. Now, with the different capacity factors, you can see that if you have a turbine, say with a 30% capacity factor, that's going to generate enough power. Each of those turbines generate enough power for 357 houses throughout a year. The rest of my slideshow is just kind of go through pictures of a construction project and kind of show you the different parts and how they're put together. If you're going to have projects out here in Sweetwater County, just to kind of see what will be happening at the time. This is the loading area. When the project is first set up, they'll set this up with the different construction trailers, and this will be, as different parts come in, if they're smaller parts, they'll be offloaded here, and this is kind of the congregating point for all the different contractors that are working. You can see there's a big pile of dirt on the southern edge of that area. That's actually the topsoil that's been scraped off. Pacificor, when we're developing our projects, we're very aware of the environment, and we want to make sure, as we're building these projects, that we're returning the sites as close to possible as the situation as they were before we started. So that topsoil is actually piled up there. Once it's done and we don't need that project management area, that topsoil will be spread back out over that area, and they'll replant the native grasses or vegetation that were there. So we're very mindful of the environment and trying to make sure that we're leaving as small a footprint as possible with our projects. So this is the nacelle. And you can see with the weight of the nacelle just how many axles you need on your truck to be able to carry these things without disrupting roadways. And so starting at the base of the turbine, this is what it looks like above ground. And this is where we start. This is actually excavated down to about 6 or 8 feet. They pour a layer of concrete down. Then they start putting on the rebar. The rebar will go, every 6 inches there'll be another layer of rebar, and it's about 5 feet where they're standing on top of the rebar above the ground level. That will all be filled in with concrete. And then this is what's left on top that they'll attach the towers to, and little box of circuits. The towers, most of our turbines have 3 tower sections, the base, the mid, and the upper section, and they're tapered, so the upper section will be thinner than the base section. They're brought in, offloaded on site, and then we have a 450-ton crane which will put the different tower sections into place. And it's a bit of a process getting them all lined up. You can see here with our towers, the blades are put together on the hub before they're installed up on the tower. See the blades on the ground. And this is what the inside of one of the towers looks like. There will be stairs going all the way up and then the different wires coming down and the electricity generated. This is one of the nacelles getting ready to get put up. So you can see it's about twice the height of a normal person. Getting put on. There's a nacelle again. Picture inside. You can see the big disc brake, which I mentioned earlier. And this is the blade. So the blades are about 120 feet long on our turbines. So see, it's a bit of a process to get them through different cities. This is the inside of the blade. The blades are hollow. They have to do a safety inspection to make sure there are no cracks in the blades before they're installed. And then you can see the lightning rod within inside the blade in this picture as well. This is a picture of the hub and all the blades attached right before it gets pulled up, put in place, and it's getting attached. That's the job that I'm on this one. You can probably see a couple little dots on that one blade that's hanging down, and those are people doing a safety inspection. Make sure there are no cracks. Once it's been up, they want to make sure that the blades are completely intact and that nothing's happened to them as they've been raised in the position, that nothing's bumped them or anything like that. If you look closely, there is a deer laying down underneath this piece of machinery. At quite a few of our sites, the wildlife are so prevalent that they come up and they'll watch during construction, especially at the Glen Rock site, which was a former coal mine for Pacificor. It was an area that wildlife had been abundant in for decades since there was no hunting as an active mining site. So they were very used to people, and they'd come up and be right around the machinery, and you'd actually have to, when you came out and went to your truck, you had to make sure there wasn't anything laying underneath your truck, because if you started, then they tend to get startled and jump up, and that causes problems. And then a herd of elk just outside one of our lines of turbines.